focus? Alright, good enough. Here we go, physics. So, small delay, right? We had a whole thing, but here we are. C-Day, or close enough to C-Day. Um, we left off talking about a new equation, right? The big equation. Um, I'd like to do kind of another problem, just to practice with it again. I realized I never posted practice problems last time, so definitely going to practice words. I'm definitely going to post practice questions this time. I'm also going to intro kind of like a new topic, and it's related to the big equation, so I don't know. Let's just get started. Um, so that was where we left off. Again, remember we have kind of like new keywords here. Let's take a look. So let's say that you had a question that said, falls from rest for 5 seconds. How far does it fall? So a ball falls from rest for 5 seconds. Now, I said before that if you look for the word drops, right, it implies that the initial velocity is 0. It implies that acceleration is lowercase g, which you can find on your reference table. I don't recall if I've said this before, but this phrase, right, from rest, that also implies that initial velocity is 0. So I know that this is 0. It's falling, right? Right here. Falls. Falling is... What the heck did I do? I don't know what I just did. Oh, that's what I did. Interesting. Okay. I should have done that. That's okay. Falling implies, again, that the acceleration is equal to g, or 9.81 meters per second squared. So I know that. The next piece of information, the time, is 5 seconds, and we want to know how far does it fall. A couple things to kind of look at here. One, when objects fall, it's because of gravity, which is why the acceleration is the acceleration due to gravity, which can be found front page of your reference table. It's in that big list of constants. Second, whenever something happens from rest, that just means it stopped. Okay. So let's take a look. Let's do some math. The change in distance is equal to the initial velocity times time plus half the acceleration times time squared. So it's equal to 0 times 5 seconds plus half of 9.81 meters per second squared times 5 seconds squared. So this first part goes to 0. That's going to be 0 plus 25. Half of 25 is 12 and a half. 12 and a half times 10-ish. All right, I'll do some real math. We'll do actual math. So 9.81 times 5 times 5 times 0.5. It's 122.6. So this is 122.6 meters. So I'm going to call it 123 meters-ish. If we fell for 123 meters. So if you let something fall for 5 seconds, assuming that it's accelerating the whole time, it's going to fall for a little more than 100 meters. I guess technically 20 meters is a lot more than 100 meters. But this was all fairly straightforward. Plug in information, we move on. I'm going to create a slightly different scenario. Slightly different because it's going to lead into our next kind of topic, which actually I could use this too, right? This situation is a situation in which something special is happening. We've released this ball and it's falling. And it's falling as a result of the acceleration due to gravity. It's the only thing that's kind of messing with it. It's the only thing acting on it. That situation, where the only acceleration acting on an object is the acceleration due to gravity, is a situation called free fall. So that is kind of where I'm going next, or where I'm going now. So we are going to talk about free fall. Right, now an object in free fall has kind of like specific conditions. First, only acceleration is g, which is, again, 9.81 meters per second squared. Right. Another thing about free fall, another thing that we do is ignore air resistance. We do this mostly for ease of calculation, because if there was air resistance, then our first statement would not be true. Right. And then eventually, I'm going to write this now. It won't make sense until we talk about projectiles, which is in a little bit, but we'll talk about this first. Yeah, I'll mention it now. So components do not influence each other, which means horizontal and vertical motion are independent. Alright, when things are falling, right? And I say falling, I mean anything that gets dropped or tossed or thrown or launched, so long as it doesn't have an engine or wings. I guess it can't be a living, a bird. A bird's not an object that would be in, well, a bird is typically not an object that would be in free fall. So if I took a ball and I threw it like this, technically it would be in free fall. We'd call it a projectile, to be a little more exact, but technically it would be in free fall. Now, free fall is unique because the only acceleration is acceleration due to gravity. I'm gonna asterisk this and make a little reminder that it points down, and that may be relevant for when we do questions. Alright? Now, in class, the very last thing, I think the very last thing that I did, was a question relating to I did a question. I think the one that I did specifically in class had to do with a car accelerating. But then I did a question about how a student throws a ball straight up at 5 meters per second. And the question is, how high does the ball go? Right? And again, we have kind of similar information here. The fact that the ball is thrown, ideally, the fact the ball is thrown straight up is actually a two-part giveaway. First, these are words are difficult to write. These are indication of free fall. So that tells me the acceleration is g. I know that this is true for this situation. I also know that the initial velocity is 5 meters per second. I'm looking for how far does the ball go, but I also don't know time. This is awkward. It's awkward because, like, I would like to know time for this scenario. Now, if you recall, I said that this is important. It points down. Because I want to look at this. I want to analyze this a little, let's take a slightly closer look at this. Specifically, let's take a closer look at this number and this number. Acceleration and velocity are unique because acceleration and velocity are vectors, which means they have a size. The acceleration size is 9.81 meters per second squared. The velocity size is 5 meters per second. But they should also have a direction. So let's make some quick adjustments because they need direction. Direction, like up and down. Mathematically, that's positive and negative. So, let's kind of take it into account, right? The acceleration due to gravity, I said just a few moments ago, points down. Which means that the acceleration due to gravity for this question is going to be negative 9.81 meters per second squared, and the velocity initial is going to be plus 5 meters per second. That's actually important. It's a relevant thing. Now, this object is in free fall. This ball that we've thrown straight up is going to do a handful of things. It's going to travel upwards at 5 meters per second initially, and it's going to slow down and slow down and slow down and slow down, and eventually it's going to come back down. In between going up and down, a very important thing happens. It stops. All right? So the fact that it stops is, again, a big deal. The reason that stopping is a big deal is because we know another thing about the ball when it's at its highest point, right? So it's traveling up and up and up and up and up and up, and it stops, and then it comes back down. But at its highest point, it must stop. And that tells us one more very essential piece of information. Because its final velocity, again, at the highest point, at its peak, because it stops, we know that its velocity is 0. Now I have two equations, and typically this means, I have two unknowns, which usually means that I need two equations. I'm gonna do this. I can use this, 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 and this. I can use the blue marks to find time, and then I can use green marks to find distance. And the reason I can do that is because I have more than one equation, right? We had, technically we've looked at 4 equations on your reference table. There's really only 3, because 2 of them are the same. But one of those equations is that acceleration is a change in velocity divided by time. Well, I know that change in velocity is... Actually, I can just skip 2. This will be the 3rd equation on your reference table. But the final velocity is initial velocity plus acceleration times time. So I know that the final velocity is 0. I know the initial velocity is 5 meters per second. I know that the acceleration is 9.81 meters per second squared. I know that the time is what I'm looking for. Now you could say plus negative 9.81. I'm saying minus 9.81 because it means the same thing. So if I do this, then I have negative 5 meters per second equals negative 9.81 meters per second squared times time. Now divide both sides by negative 9.81 meters per second squared That cancels, and this tells me that t is not quite 2. I'm betting it's like 1.8. I'm going to do the math. So 5 divided by 9.81. Nope, not minus. Nope. Alright, hang on. 5 divided by 9.81. There we go. 0.51 seconds. So what we have is 0.51 seconds. This is how long. And this is the time to the top. Right? Because again, I know that it's traveling a certain speed. It has to get up to the top. I'm looking for how far does it go at the top. So I have to go from its initial spot and its final spot. I'm considering the very top. I know that it stops at the top. So it takes 0.51 seconds to get to the top. Now, I can do... just kidding. I can do the change in distance is initial velocity times time plus 1/2 acceleration times time squared. And now I have all my information. It's 5 meters per second times 0.51 seconds plus half, and I'm going to move the screen over so that we can see. There we go. Plus half of negative 9.81 meters per second squared times 0.51 seconds squared. So, again, math. 5 times 0.51 is, the first part here is 2.55 meters plus 0.5 times 9.81 times 0.51 times 0.51. And this is going to be plus, actually, really it's going to be minus, right? So I'll do plus negative. So plus negative 1.2757905 meters. So, and then again, back to here. This is going to be give or take 1.2742 blah 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 stuff meters. I will round that to be about 1.3 meters. So our ball, when all is said and done, will travel about 1.3 meters off the ground. Or 1.3 meters from wherever it was released, right? Which kind of makes sense. 5 meters per second is fairly slow for a ball. 1.3 meters is not that high. It's like 5 feet. 4 feet. 4.5 feet, give or take. So that's not that high. But the key here was twofold. One, we threw the ball straight up at a speed. And because the question asked how high the ball went, we knew that our final spot was the very top, the peak. At the peak, the unique thing is that for that infinitesimally small amount of time, it stops. It's suspended in midair, and then it will fall down. But it's going up, slowing down, slowing down, slowing down, slowing down, slowing down. It stops. Stops at the peak. Using that information, the fact that it stops at the peak, I can find out how long the ball is in the air. I can figure out how long it takes to get to the top. Then once I have that, I can use my big equation to figure out how high the ball goes. Right? Now, what I'm going to do, right, is post probably 3 practice questions. One of them is going to look like this one. One of them is going to be an up and down question. The other 2 will probably be a left-right question and then maybe a straight-down question. But it's going to be 3 practice questions eventually using the big equation. All right, it'll get posted. You'll see directions. Hopefully, we don't have too many more interruptions between now and the end of the marking period, although I know that there are many interruptions. It is what it is. In the meantime, physics, please make sure to do the questions and submit online. You'll see the directions on my CBA. Take care, y'all.